welcome everyone. Welcome to the final session of the workshop. First talk of the final session is computing the independence polynomial in Shearer's region for the LLL, and Nick Harvey will lead it.
All right. So we'll be talking again about polynomials, my favorite topic, and this is joint work with Piyush Srivastava and Jan Vondrak. So I'm going to start with a statement of the LLL, since we're sort of a mixed audience here. So I presume many of you will know this, and some of you may not. So the Lovász local lemma is a famous tool in probabilistic combinatorics, and can be stated as follows. So if you have events, E1, E2, and so on, in a probability space, and you assume a certain dependency structure on the events. So if each event is independent of all but a small number of other events, the most d other events, and you know that each event is not too likely, so each event occurs with probability at most 1 over e times d plus 1, then the Lovász local lemma asserts that it's possible to avoid all of the events. So the probability of the intersection of the complements of the events is strictly positive. Okay. And so it's kind of an interesting phenomenon here is that it's sort of viewed as a non-constructive tool, right? It's showing the existence of this point in the intersection of the complements of the events, but the probability of that set could be exponentially small. So if you tried just drawing random samples to find such a point, then it could take an exponentially long time to find it. So think of it as this needle in a haystack type problem. Okay, so let me give an example of this. So simple example, two colorability of hypergraph. So we have a set system or a hypergraph, and we assume that each hyperedge has bounded size, so size at most k. And we also assume that each hyperedge intersects not too many other hyperedges. So each hyperedge intersects at most 1 over 2e times 2 to the k hyperedges. And our goal is to color the nodes of this hypergraph with two colors, red and blue. And our goal is to avoid having monochromatic edges. So we want that every hyperedge should contain both colors, red and blue. Okay, so one thing we could, so to set up our probability space to discuss the local lemma, we're just going to take a uniformly random coloring. So imagine independently coloring the nodes red and blue. Okay, so let's see how the LLL applies in this case. So for each, so we need to define some events that we'd like to avoid. The events will correspond to the hyperedges being badly colored. So we say that event EI occurs if the hyperedge AI is monochromatic, all red or all blue. And now we have a nice dependency structure on the events because of our assumption that each hyperedge intersects a small number of other hyperedges. So because of that, we obtain that every event EI is independent of all events EJ where those two sets do not intersect, where they don't share a node. Okay, and then we need to check the parameters of the local lemma. So because we assume that there's this restriction on the intersections, then we know, so the D parameter on the previous slide, the number of events that an event is dependent on is bounded, right? So we get this bound D plus 1 is at most 1 over e times 2 to the k minus 1. Now we've chosen the parameters carefully so that if you look at the probability of an event occurring, so the probability that an edge is badly colored is 2 to the 1 minus k, right? 2 to the minus k is the probability of each coloring, and there's two bad colorings, all red and all blue. So that's the probability of the bad events, and the parameters are chosen so that the inequality we need is satisfied. And so the hypotheses of the LLL are satisfied, and that tells us that there's positive probability that no hyperedge is monochromatic. But this probability will typically be exponentially small, And so that's what we will need to deal with. OK, so then the question is, how can you find such a good coloring, right? How can we make an algorithmic version of the LLL? So there's been a long history of work on this problem, dating back to work of Beck, and then many, many improvements on this. It's a long list. I've probably missed many from this list. And there was a big breakthrough in 2008 with this algorithm of Moser. And what Moser said is that he gave this simple algorithm, basically just look for any hyperedge that's badly colored and recolor it randomly. So here we have a blue hyperedge that's badly colored. We randomly recolor it. Now we find this red one that's badly colored, and then this one. And we keep going, and then eventually it converges to a good coloring. So their theorem is that if the hypotheses that we had are satisfied, then this algorithm will terminate in expected polynomial time. OK, so now let's step back a bit, and let's sort of take a high-level view of the previous algorithms for the local lemma. So essentially, all of them are of that same sort as the Moser algorithm I just described. So if we think of the space of possible colorings, so I have my cube here of colorings, then we have some feasible region of good colorings. And what the algorithm is doing is it's randomly generating integral points, these colorings, is randomly generating colorings until it lands in the feasible set. So it randomly picks some coloring, which is not good, randomly picks some other coloring and some other coloring, and eventually the convergence guarantee is that eventually you will find a coloring that lands in this feasible set. OK, so the first message I'd like you to take away from this talk is that we can do something different here. That we can take a different view of the dynamics of an algorithm for the LLL. So what we will do is basically a rounding algorithm for the LLL. So what we will do is we'll start with a feasible fractional coloring. So throughout, I'm just going to be talking about hypergraph coloring instead of talking about general probability spaces. So that'll be our running example. So we'll start with a fractional coloring for this hypergraph coloring problem. Then what we will do is we will perturb the coordinates. We will round each coordinates one by one until they're integral while maintaining feasibility. Well, we're still in this feasible region. OK, so we make the first coordinate integral, second coordinate integral, and then we stop when we land at a vertex in the feasible region. OK, so that's going to be our approach. OK, so now I need to introduce some more notation. So we talked about the sort of the dependency structure that the local lemma needs. So if we start with this hypergraph coloring problem, we need to define the notion of a dependency graph. So we will have a vertex corresponding to every hyperedge that needs to be colored. And then the edges in the dependency graph, so indicating these events that depend on each other, those come from hyperedges that intersect, as we said before. So hyperedges that intersect yield edges in the dependency graph. And we know that the maximum degree in the dependency graph is at most d because we have this bounded independence property. OK, so let me make one observation that we will return to later. Let's observe that if I fix a particular node in the hypergraph, so let's say this node in the corner here. So this is a node that we're going to color. And I look at all the hyperedges containing that node. They form a clique because of our definition of this dependency structure. Right? So if I have these three sets, then I have a three clique on those vertices in the dependency graph. Does that make sense? OK, remember that fact, because we will come back to it. OK, now here come the polynomials. So what we're going to look at is the independence polynomial of this dependency graph. And actually, it'll be the multivariate independence polynomial with alternating signs. So I'm going to stick in a minus sign there. So we have a real parameter, or even complex, as we'll see later. But we have this parameter PV for each vertex in the dependency graph, corresponding to the hyperedges. and then we sum over all the independent sets the product of those corresponding variables in the independent set. Okay, so back to this feasible region in the previous picture, this purple region that we were trying to stay within. So what is this feasible region? I said it was the region of good colorings, but then we had fractional points inside it, and I didn't tell you what the fractional points are. So here's actually how we will define the feasible region. So it's called the Shearer region, and it's defined using these independence polynomials. So here's the definition. So basically, the independence polynomial at every point p prime that is majorized by the point p must be strictly positive. Okay, so you can think of it as we're avoiding zeros of the independence polynomial in a certain strong sense. So essentially, I mean, there's many equivalent definitions of it. You can also think of it as if you think of the dividing the space into regions defined by the zeros of this independence polynomial, then we're looking at the connected component containing the origin. That's the Shearer region. Okay, so Shearer, who defined this, stated the following strong form of the Lovász local lemma. So if you have these events where pi is the probability of event ei, and then you have this dependency structure defined by this dependency graph, then as long as this vector p of probabilities lies in this Shearer region, then the conclusion of the local lemma holds. You can avoid all the events with positive probability. And it's a precise characterization in that the statement is false for all points outside of the Shearer region. Okay, so the Shearer region is a bit hard to visualize, so let's just think of the univariate version. So we'll just restrict to the case where all the pi values are the same. So, and then let's define the minimum root, so the root closest to the origin of this independence polynomial. Let's call that lambda g. So we know that the independence polynomial, it's a univariate. It has no roots in this region up to lambda g. And then after that point, it can have plenty of roots. So what Shearer's lemma is saying is if your probabilities lie in this blue region, then the conclusion of the local lemma is true. And then once you're past that region, then the conclusion of the local lemma is false. And it's also interesting to characterize, to look at what happens restricting to degree d graphs, so graphs of maximum degree d. So if we let lambda prime sub d be the smallest value of that lambda g, so the closest root to the origin over all graphs of maximum degree d, then, and then we call that lambda prime d, then the value of that is precisely known, and it's about 1 over ed. And that 1 over ed is no coincidence. That's essentially the same value that showed up in the original form of the local lemma, slightly better. OK, so now that we know what this feasible region is, let's talk about our rounding approach to the local lemma. And again, just restricting to the example of hypergraph coloring. So here's our algorithm. It's essentially as simple as can be. So we're starting with this initial random coloring, the uninformative coloring, where everything's half red and half blue. Then all we do is examine the nodes of the hypergraph one by one, and we color them either red or blue, whichever will preserve feasibility in this set, in this Shearer region. And then once that's done, then you just return that coloring. OK, so that is our local lemma algorithm. And so we need to prove two things. First of all, that such a choice of coloring is always possible, that you cannot always preserve feasibility in the Shearer region. And then second of all, algorithmically, how can you make such a decision? OK, so first, let's start with the existential question. OK, so remember our definitions. We have our independence polynomial in our Shearer region. The first thing I'm going to do is cheat. So because we had this sort of complicated majorization condition, which really it just adds confusion and doesn't really add much difficulty to the proof. So it just sort of complicates the notation. And to keep things simple in the talk, I'm just going to ignore it. So the crux of the proof is really just this case with this simpler set. OK. So then we also had this definition. PV is the probability that our hyperedge A sub v is monochromatic. So now let's look at how that can be expressed in terms of the coloring probabilities of the variables. Remember, the algorithm is perturbing those. So let's let xu be the probability that we color node u red. Then this PV, this probability of being monochromatic, is just the probability that your hyperedge is all red or all blue. So we can write it this expression in terms of the x variables. Okay. And one observation is that this is a multilinear polynomial in x, right? So the probabilities of the events being bad is a multilinear polynomial in the coloring probabilities of the nodes. OK, now remember that observation I asked you to remember earlier? So let's go to that. So we said that the hyperedges containing a particular node u form a clique. And so that means that the vertices v for which this PV polynomial depend on a particular xu value, the particular xu variable, those vertices of the dependency graph form a clique. All right. Now, as Mika used in his talk yesterday, this useful fact that independent sets and cliques intersect in at most one vertex. So we have this clique of vertices that depend on each particular xu value. But then if we look at the independence polynomial, it's summing over products where the products are over independent sets. So every monomial that appears in this sum can only have a single copy of x sub u. And therefore, the whole polynomial q is also multilinear in x. Right. So now when we're doing the rounding, if we're increasing the probability of a node being u, then q is changing linearly in our perturbation of x sub u. So that means that one of those two directions is going to make q go up. Right? And therefore, since our cheating version of the Shearer region just requires q to be positive, one of those two directions is going to preserve positivity of q. OK. So that is a proof of the local lemma modulo the small amount of cheating.
So once you have an integral thing, why is it obviously true that everything is satisfied given the polynomial?
Ah, OK, OK. So you need a bit of care there as well that relates to the cheating. So essentially what the cheating is saying. What the cheating is saying is that even if you look at the probability of small sets of events occurring, you have control over those. So essentially, if I choose a certain p prime value, then essentially I want to choose the p prime value to be supported on a single set. Have support size 1, and that will tell you that each of the individual events does not occur. OK, so it's a bit hard to see because I haven't explained the cheat, but the same reason why the cheating is justified is the same reason that justifies that the events don't occur. OK, so we can talk about that afterwards. OK. All right, so let's now get to the algorithmic question. So I'll state our main algorithmic results. So what we need to do here is we need to do this coloring to preserve feasibility in the Shearer region. And so what we need to do is to be able to test membership in the Shearer region, right? We want to know which of these two directions is going to preserve the feasibility. So the main ingredient is an FP-TAS for the independence polynomial. And our FP-TAS works, the region within which it works is exactly the Shearer region up to this small slack parameter that we need. So our statement is, so if you have any point P such that if you blow it up by a factor of 1 plus alpha, so you have a little bit of slack and it's still in the Shearer region, then there's a deterministic algorithm to compute a 1 plus epsilon approximation, so an FP-TAS for Q evaluated at the point P in the following runtime. So basically n over epsilon alpha to the power of log d divided by square root alpha in the exponent. So for constant amounts of slack, then you're getting, in constant degree graphs, then it's a polynomial time algorithm. I hesitate a bit to call it an FP-TAS because of these, parameters in the exponent, but you can think of it as an FP-TAS. Okay, so all right. So why might you be interested in such a thing? Well, so this relates to statistical physics, as we'll see on the next slide. So people are interested in computing the roots of this independence polynomial, even for fixed concrete graphs. So for example, for the integer lattice in the plane, physicists are interested in studying exactly the location of the root, and there are papers giving lengthy calculations of lengthy estimates of this root. So potentially, this FP-TAS could also be useful to physicists. But how we're going to use it is in the following way. So we can use it as a membership tester for the Shearer region. So we can give, so it now becomes a quasi-polynomial time algorithm. So runtime something like n to the root n for deciding membership in the Shearer region. And so we end up with something similar for the LLL. So suppose you have an LLL scenario with m variables such that the event probabilities lie in the Shearer region with slack alpha, then we can give a deterministic algorithm to construct a point avoiding all the bad events. Again, in time, sub-exponential in the parameters n and m. So the runtime basically, n to the root m log d. Compared to previous algorithms that you may have seen for the local lemma, so previous randomized algorithms are certainly much better. So we have polynomial time algorithms, polynomial time randomized algorithms, and then there's also deterministic algorithms under some stronger hypotheses that also run in polynomial time. But I think the interesting message here is that the viewpoint of our algorithm is different, right? So instead of doing these random resamplings, we're using the power of polynomials to gradually round to a solution. Okay, so I just have one more minute. So let me talk a little bit about the statistical physics connection here. So in statistical physics, people are interested in studying the independence polynomial. And so they would define it in the following way as this partition function, which is essentially you remove the alternating signs from our definition, and let's just restrict to the univariate case. So there are many connections between counting algorithms. So on the computational side, algorithms for evaluating this thing, and in the physics world, thresholds for phase transitions occurring. And so there's this celebrated work of Weitz and Sly. So Weitz showed that for positive real parameters, you can get an FP-TAS up to this certain threshold, which is meaningful in physics. And then Sly's result is that beyond that threshold, it's NP hard to compute it. So our work can be viewed in this context as looking at what happens on the negative axis and even in more generally in the complex plane for evaluating this partition function. So it's known that for sufficiently negative parameters, it's again NP hard, but our FP-TAS goes exactly up to that point where the NP hardness kicks in, and so we can, so we now have a complete understanding on the real line of where computing this thing is NP hard versus where you can get an FP-TAS. Okay.
Sorry, there seems to be this region where it's NP hard, but
okay. So, I mean, this is a little bit confusing because it's about how you quantify over the graphs. So for any fixed graph, our FP-TAS can go up to this graph-specific parameter, the closest root to the origin for that particular graph.
Okay.
But then if you quantify over all deregular graphs, then potentially you get moved in a little bit. Okay. So just the last word. So the technique here, so Weitz's technique is using the correlation decay technique. And our work actually our algorithm is the same. It's the same as Weitz's algorithm, but we prove a multivariate and complex valued generalization of that same algorithm. Okay, so I'll finish there.
So, besides the approximation by 1/e, you showed the true value d minus 1 to d. Is that also coming from the d or d minus 1 branch in tree?
Yes. Yes, exactly. So if you can do a sort of a univariate version of our proof, and exactly this d minus 1 to the d minus 1 over d to the d parameter will come out as the the limit, or the limit to within which you get this correlation decay when you recursively compute the values on this tree. Exactly.
So the Shearer polynomial, it gives you an exact characterization of the LLL.
Yes.
Imagine you allow yourself a lot of slack. Do you know an easier potential function that you can just follow?
Imagine if you allowed yourself a lot of. I see. So you didn't want to work in the exact Shearer region, but you wanted to work in a more restricted region.
Yeah, let's say for your hypergraph case, I don't want my 2 to the k many hyper edges. Some
I see. Yes. No, okay, that's a very good question. Yeah, so I don't have a proposed potential function. Indeed, it seems like further progress in this area might, that might be a nice direction for it. Because for us, the main difficulty is dealing with this FP-TAS, right? That's what's making our algorithm slow. And so if you had a better potential function, then maybe you could get a faster algorithm.
So I don't understand, like your dependence on epsilon was very mild, right? Like those parameters?
Yes, just 1 over epsilon.
So can't you assume it's like half and half or something? I mean, like why do you get the such?
Okay. So in the LLL algorithm, we never evaluated to high precision, actually. So I think we only use it up to constant. Like take epsilon to be half. I think that's all we use in the LLL algorithm.
So doesn't that mean if you have slack, you get polytime?
No. Yeah. So there's two parameters: the epsilon and the alpha. The epsilon we're happy to take to be half. The alpha. Okay. So this is sort of the trouble is that our FP-TAS did not have an n or an m in the exponent. but the LLL algorithm does. So there's some difficulty in the reduction of how the LLL algorithm uses the FP-TAS that causes the slack parameter to get much worse. So we can talk about that offline.
Let's thank them.